Good morning, everyone. Like IBM and NASA, like in partnership with NASA and Oak Ridge National Laboratory, we developed a Prithvi weather and climate foundation model for weather and climate downstream task. Just to start with, one second. Is my screen moving? Yeah. So, yeah, just to start with that, actually, we have a variants of foundation models called Prithvi and Granite family of geospatial models. So we have called Prithvi with different parameters like 100 million, 300 million. So that's mostly for the Earth observation satellite data. And so this talk will be on Prithvi weather and climate. So here we focus on downstream tasks in like weather and climate, like forecasting, hurricane track predictions, gravity wave parameterization, and downscaling um, uh, features. So just to want to highlight, so this developed by a team in IBM Research. These are the like core team members, and then from NASA, and then we have from people from Oak Ridge National Laboratory. And although I was not part of the core team, I'll try to cover the gist of the work. So yeah, so just to start with, maybe you guys might be already having the conversation about the foundation models. Maybe I don't have to go in deep detail, but just to give a high level that like there are like a two kind of revolutions, right? So one is on the language and vision side, we have a foundation models, and on the other side we have a forecast emulators, which basically can capture the atmospheric process and it has a an advantage of having higher computational speed. I mean, with low computation resource and and the other side, the foundation models are very good at predicting the sequence, right? So something like this, and if we can mask some words, and it is good at predicting what is a like mask word, right? So like we want to bring it based of these two world, right? So these foundation models are generally it's basically to generalize to and basically to learn the general representation, right? So generally like we try to build like when we are looking at the deep learning era, right? So when we try to have a one task specific models, right? If it's a segmentation, if it's a classification, we try to build specific models, but foundation models, so this actually helps in learning general representation. And for the given task, we don't have to put much heavy resource in learning, right? So we can just fine tune with a small data set, right? So that's the idea about it. So this can be applicable to multiple use cases, right? And also it has advantage that since we are sort of like masking thing, and then we are trying to reconstruct the mask pixels or mask words, right? So this has advantage of recovering the missing informations. Yeah, and on the other side, yeah, the forecast emulators generally, they try to model that physical process, right? So yeah, so this work, if we try to bring the best of these two worlds, basically we want to combine both things, right? Um, so yeah, when we look at the literature, I think this work was like in IBM actually like more than a year. I mean, I think we have been working on this thread. So I think when our team, when they looked into the state of art, so what they observed is that like most of the emulators, right, AI emulators, and most of the work are focusing on forecasting part, right? Yeah, so these are like list of applications, right? Common applications in weather and climate space, but we realized it's mostly on the forecast part. What we actually, I mean, wanted to see is that like beyond the forecast, so we have other applications, right? Like kind of downscaling. We wanted to increase the resolution of the data, and if you want to predict the hurricane, severity, we want to do a gravity wave parameterization, right? Like in addition to the forecast, like we have other tasks, downstream tasks, right? So the idea is that, like, how you can actually have a like one foundation model which can, can do the perform the forecasting, as well as it can do the segmentation, prediction, and downscaling, right? So that's a motivation, like why we started this work. So she started collaborating with NASA. So NASA actually has a Mira to reanalysis data. So yeah, we started with this data set. So basically from for like last 40 years data set of 1980 to 2019. So we collected, I mean, 40 years of 3 hourly Mira to reanalysis data. So these are so we collected like around 160 input variables. So here actually we also wanted to, like, incorporate the forecasting part, right? So we have actually added timestamps of 2. So that's why we see the 320 dynamic input variables. So this includes 20 surface level parameters and 10 vertical level parameters, and then 14 like for model levels, right? Different pressure levels. So yeah, what you see here, these are the type of data, and then so we listed the variables here for different model levels. And here also we also included the climatology data. So that's basically what it means is that, like, suppose we are interested in particular parameter, right, X. So and then we are interested in, like, predicting, maybe forecasting what will be the value at t+1 time. So we wanted to see the way what the variation for last 20 years for that parameter at that particular hour. So that that variation part actually we try to incorporate in our objective. So that's the climatology data talking about here. And in terms of pre-processing, like, yeah, so we just did like for few parameters, yeah, the data was not available at hourly level, so it was like for some 30 minutes was there, so we just try to, like, average it and then, like, get at hourly level. Like, apart from that, like, we use rest of the data as it is. Yeah, so these are the training strategy. So yeah, it's yeah, variant of, like, even VIT, I mean, vision transformer only. So the yeah, here the objective is that, like, okay, so we have a two timestamp, right? X t and t-1, and we need to also we need to capture the what is the, the lead time, the lag time, right? Whether it's a the difference between the t and t-j is whether 3 hours or 6 hours, 9 hours, 12 hours, right? So we taken all the cases, and we wanted to encode this data, and then we got to basically, before that we want to mask some of the sequence some of the data points, and then we encode it, and then whichever the mass data, like, we wanted to reconstruct that using the decoder, right? So and here, like, for the forecast, so again we have like different forecasted hours there, like, so we wanted to, like, have 6 hours, 12 hour, 24 hours. So these are the, like, I mean, kind of variations, right? So we have a spatial data, and then we have a temporal part, and also we have a lag between that input data, and then the output targeted data also, we can have a different um, forecasted time, right? So yeah, so now actually, like, yeah, so this is a setup, right? So now we wanted to okay, so before that, like, I mean, why we need to do masking, right? So I mean, in this case, like, I mean, how it can help, right? So yeah, one is, okay, so since data has some missing data, or could be sparsity might be there. So having I mean, if you mask it, like, when you try to reconstruct, the model will try to learn from that, existing pixel, right? Suppose we have like only 5% pixels are like, valid pixels, whether we can, regenerate the rest of the 95% of pixels from that and all, right? So that sort of capability the model will have it. And yeah, another advantage is about the GPU memory pressure, right? So having, if you mask it, like, only the, like, unmasked pixels will be processed by the encoders, and right, and then the so yeah, that way, like, we have the memory is when we're consuming less memory. And yeah, so the another part is like, so we need to have a like, zero lead time. So what it means is that so generally the forecasting problem, like, we try to learn, so what is the like kind of way, I mean, difference between the t and t minus j instant, right? But since like we wanted to formulate like I mean, we wanted to jointly formulate forecast problem plus um, t equal to zero. Basically, if it's some segmentation or if it's like downscaling, there's no time part, right? T equal to zero. So we wanted to have that variant as well. So yeah, here like masking will help that to learn reconstruct the pixels, right? Okay, so yeah, so the idea is that like once you have that pre-trained model, like we can actually leverage the encoder part, and then the decoder could be based on the task specific, right? So it could be a regression task, it could be a segmentation task, right? Okay, so yeah, so here's the interesting part. Um, so what we try to do, I mean, and how we actually handle it is here, right? So when you look at the, like basic objective generally, right? If we are forecasting problem, so what we try to do is like we wanted to get a like value x t plus one time. So it's generally it's a function of just the like xt, I mean, yeah, current time, and then maybe the previous time instant, right? And then we try to normalize that. So that's what generally the, I mean, basic objective. And like another variant of is that like we try to look at the what is the rate of change between like current time and then the forecasted time, right? So that we try to learn, so that yeah, and like, again it's only function of current time xt and then the like previous time xt minus 1. So this is a, I mean, good for like, maybe the forecasting problem. But so what we try to include, right? So we also wanted to have zero lead time. So basically when t is I mean when we don't, yeah, when the delta is zero, right? So that in that case, like this objective function will not valid, right? So what, yeah, because the difference will be zero, right? So what we did is that like we incorporated this climatology data. So basically the C part, what you see here, right? So we are, I mean, we are not looking at the difference between x, the forecasted with not the current value. So instead of that, we're looking at for this t plus I instant, maybe this something like a kind of like third hour, right? Maybe like a third hour, right? Maybe in the day, a given day. And then for that given Julian day, third hour, we're trying to look last 20 years data. Like, so what is the variance in that, right? So we try to like, capture that, that difference. So we try to model it, in that way, like, by incorporating the climatology data. So here when you see here, like, and also like we also wanted to have different lead time, right? So we want like, see here you see the I part. So this is like for different lead time, and J is like for different forecasted time. So yeah, so here yeah, the thing actually we actually sort of like introduced here is that like we try to incorporate this climatology data for last 20 years. So that way, so this objective function will be valid for forecasting problem as well as valid for like non-forecasting problems, right? And which where we can have a variant of different lead time and different forecasted forecast head time, right? So that's what we try to incorporate here. Okay, so going to the architecture, right? So yeah, so here, like now we have a two data for given a feature, like we have a at current t and then t minus j, like with any lead time, any lag, right? So we have a two timestamp data points. So what we did is at like now we created a windows. So here the window size is, yeah, it's a again hyperparameter. Like this is some 30 cross 32. That is a window size, and we consider each token as 2 cross 2 pixels. So what we try to do is that like we wanted to learn like local dynamics as well as the global dynamics. So basically, we want to capture the local context and local context, local and then the global context. So what we try to do is that like we try to have two masking strategy. So within the window, like if you do masking, that's called we calling yeah that's like local masking, and we try to reconstruct that. And across the windows, right? So like when you mask the entire window, so that is calling as global masking. So yeah, when we apply both local masking and global masking, so then we want to perform local attention, global attention. So basically, for that local masking, we want to perform local attention. So yeah, the idea here is that if you just do a self attention for all the pixels to pixels, like it's kind of like quadratic, right? So like but if you do a kind of a local attention, it will be a kind of a linear. So that's the idea here. But also like we are learning the local dynamics within the window, and with the help of global masking, we also learning across the windows, right? So we get the global context as well. And here so this is around 2.3 billion parameter model. So we have 25 encoders and five decoders. And yeah, so in the 25 encoders, like we had a combination of like local attention and global attention. So start with local attention. So we have around 13 encoder layer where we apply local attention, and then the remaining 12 layers we apply the global attention. So, and similarly for decoders, total we have like a five decoders. So again, start with the local attention. So we have like three local attention and then two global attention. Yeah, so this way actually, we try to, mask it and local and then the global, and then try to reconstruct the mask values in local and global. Okay. So that's what we try, this is our like the overall architecture. And so yeah, so this looks good, right, for forecasting, because and I know we also wanted to like suppose yeah if you okay, this is like masking strategy, and like if you wanted to do some extended pre-training where we wanted to focus on like particular lead time or right a forecasted time, um, then like then maybe we don't need to like apply a masking strategy, right? Okay, so first there are two phases, right? First we mask it and then you learn, right, one model. Then we wanted to have a another extended pre-trained model that can be very focused for forecasting problem for given lead time. So for that, like the so we try to use the spin and transformer like approach. So since like if we don't do any masking, and so instead of having this local attention and global attention, like in the next second stage of extended pre-training, so we can actually introduce a spin-like shift. So that's basically we can have an overlap of the window, and then like you apply your attention, right? So that way, so the pixels will be in there, like in adjacent windows that will overlap. So that way it will try to learn. So yeah, we had like kind of it's sort of optional, the spin like shift, but the base model will be just based on the like, local and global attention. And this could be very focused on like we have some one foundation model, then we wanted to have an extended pre-trained version of that model for any particular time, um, lead time, or like any particular um, forecasted time horizon, right? So there actually we can apply the spin like shift. So yeah, so we had like a two version of the model. So first stage, as I mentioned, so it's a 2.3 billion model, two timestamps, and for this, input lag time like 12 hours, 9 hours, 6 hours, and 3 hours, and the output step is a forecasted time. Like it start with zero, so zero applicable to downscaling and segmentation task, prediction task, and we have for a different forecasted time horizons. Um, and here actually we applied 50% masking. So yeah, we also released this checkpoint. It's in hugging phase. Um, so in the another version of model, so where that one we calling it as rollout. So where, here actually we, without masking, right, we applied the this encoder decoder shift, and then here actually we're fixing the input step to 6 hours the lag, and then the output also 6 hours ahead. And so this actually we kind of extended pre-train because we want to see that, the performance for the forecasting problem. So we observed that, like, doing this experiment, and having another like version of model specifically for particular input and output step, like we found that, like, this is better for forecasting problem. And this model is sort of general model for forecasting plus other applications, other downstream tasks. But this one, if we found that, it's sort of like kind of you can call it like kind of extended fine tune and sort of fine tuning, but like, but we didn't added any new decoder and all, but it's sort of extended pre-training. That's why we call it like a rollout. um, so there are like, yeah, I just took some snapshot of the results. Like, I mean, we have a paper in archive, like where detailed results are there. So here we're trying to show that, like, some zero shot reconstruction. So basically we're having a local, masking and the global masking. So the and at a different lead time, 0 or 6 hours. We're trying to see that how the RMSE values with respect to masking ratio, right? Yeah, so yeah, we see that, like, I mean, yeah, it's sort of like if you higher the masking, so we increase from 40% to 99% to see like how the RMSEs are, like, varying. Yeah, so you could observe that, right, for local masking, the RMSE are lower, and for global masking, you see the RMSE values are like little higher, right? And yeah, so if for lower masking ratio, the difference between the lead time is not very much, right? Sorry, yeah, it's the other way around. For like for high masking ratio, the lead time is not actually playing much role. So, but yeah, but the good thing is, like, we could see that, the RMS's the values are like, within the expected limit. And similarly, we try to do like zero shot forecasting performance. So here actually we try to compare with other existing models like GraphCast, Punku Weather, and but one difference is that, like, it's not actually maybe apple to apple comparison, because in the Prithvi WX. Uh, so yeah, so here actually, like, we Prithvi, we are using a Mira 2 data set, but for other models, like, I think we didn't come across, like, other paper, any other literature that are using actually Mira data set. But like, we took from the ERA data set, but maybe the special resolution is very high, but still we wanted to see that whether it's in the range or not. But yeah, so for like for temperature at 2 meter, like, we see that, it is almost like comparable. Although, like, the Mira data set is which the resolution of like zero point 0.5 degree latitude, and like 0.625 for longitude, compared to ERA data sets like 0.25 degree, close to 0.25 degree, right? So yeah, and then yeah, some few snapshot, like, I try to put it here to show that, like, we try to for different variables, we try to apply masking strategy to see how um, like how good at reconstructing that mask pixels. Um, yeah, so what you see here, like, this was 75% masking, and then we try to, when we're just showing it visually, but the RMSE numbers are in the paper. So, and then we try to also see, like, increasing to 95% mask. And yeah, so this is for the reconstruction looks like. Um, and this is for another parameter, temperature 2 meter vertical. Okay, so and okay, I also like to show some notebook. Like, so if you are interested to play with this model, so we already actually open sourced it, so it's in Hugging Face. So maybe I can show like few notebooks. think we have time, like, yeah, I'd like to show some few notebooks, like if you wanted to, like, want to do fine tuning for like particular applications, like maybe you want to do a downscale scaling, or you wanted to see the zero shot. So we have some notebooks. So if you see in the GitHub, like, we have a two versions. One is from NASA Impact. We have zero shot examples are here. So when there's a good documentation, so like I just wanted to show the example. So yeah, so this is about zero shot reconstructions. Yeah, so yeah, the way maybe I just want to show that how the data looks like and all. So basically, so these are the data. Okay, yeah. So these are the surface variables and static variables, and then the vertical variables for different levels, 14 levels. And yeah, so you'll find the data set also, like we have, sharing it in the Hugging Face. So you'll find the data set here called Mira 2, and we have a checkpoints here, right? And then we have a config file. So yeah, if using that, actually we can run the inference. So yeah, basically you download the data, and then also this climatology data. So that also we actually processed. It is in the Hugging Face, so that also you can actually download it here. So once you have that, you can yeah. So prepare the data set. Okay. So yeah, and then you can call, yeah, you can load the model. Okay. Yeah, so this is the model definition. So basically the config file it's part of that Hugging Face. So once you have a config file, so all the informations about the model parameters all will be there in the config file. So you can actually initialize the model. So once you initialize the model and you, yeah, load the weights, so basically backbone weights, and then you can perform the zero shot learning. Um, So yeah, it'll be hands-on. Like if you if you guys are interested in playing with this model, and we have other examples for rollout as well. Like so this is for um, I guess like the second stage of pre-training, right? So where we wanted to focus only on the forecasting problem. So this will be a similar thing. So only the difference will be that like we have to define like what is the lead time we wanted to forecast, right? What is the input time, and then what is the lead time? So here the input time is like 6, and then like lead time is like 12 hours. So we wanted to forecast. So these two examples are for zero shot learning. And so there is another repo, like yeah, this is under NASA Impact org. And there's another repo called another org, you see under IBM org, Granite Weather and Climate, WxC, another repo. So here we have some examples for downstream task. So let me just quickly show that as well. Maybe it's useful. So here actually we took um, yeah, environment climate data for from Canada. Like so here we got the ground truth. So we have a two different resolution. It's in the order of like 8x. So we try to leverage this data set to see how good we can do the downscaling, right? Um, so you'll find notebook called ECC downscaling fine tune. So basically using this file, you can actually notebook, you can fine tune your model. Okay. So yeah, again, so basically the important thing is like, yeah, you need to download the data and also that, uh, so we actually already, yeah, so you get the uh, model weights here, and then yeah, the data is also part of the repo. So I think you'll find it easy and playing with this notebook. Yeah. So yeah, we sort of like created a wrapper around most of the things. So a few lines of code, you should be able to fine tune the model for any other data set as well, right? So yeah, this is how that just doing snapshot of that how the training and validation loss. So once you fine tune the model, so you can actually do the inferencing. Um, yeah. So yeah, one thing is that like you need to actually define the config file. So this is the config file here. So here we just showed that since it's fine tuning, right, you can have any decoder head. So here we added a unit. So for the sample example, so here you need to define that, where are your, data sets are there, and what is your downsample factor you wanted to do, and then other like model related parameters like where the models are located, right? So it's mostly like, if you can actually play with the YAML file. Once you given configure the YAML file, you can directly run with these notebooks. It's more handy in the sense. Okay, so also another thing I just wanted to share is that like, so we also have a open source library called TerraTouch. Not sure like how many of you used it. So here actually, this is very specific to fine tuning framework for geospatial foundation models. Like we support, apart from IBM foundation models, like other foundation model like Clay and like, so most of the foundation models are like, we try to support it here. But the idea here is that like, if you wanted to build on your own, like, new fine tuning framework, so you need to maybe you to use some PyTorch Lightning library and then some Torch Geo libraries and all, right? So, but here we try to create abstract, based on PyTorch Lightning and then the Torch Geo. So, like in a few lines of code, you can like create a Python notebook, or otherwise like even like one liner you wanted to like run, right? So we have a YAML file like I showed. So you can actually give that all the like data location, everything, and then like you can do this fine tuning in like in the console itself, like TerraTouch fit means and then you give the YAML file, it will run the fine tuning part. Like if you want to do inferencing, TerraTouch test. So yeah, we try to create a more abstract, so you don't have to like spend time on like writing a Python code and for like fine tuning and or inferencing, right? So this could be very handy, like, if you're interested, like you can, yeah, explore this library called TerraTouch. And we have a lot of examples here. And yeah, this is completely open sourced from IBM. Okay, maybe I'll pause it here for any questions. Yeah, so I was some advertisement about, I think, coming AGU. Actually, we have a session like accepted. Like, if you guys are interested, like, please submit your work. So here we're focusing on geospatial foundation models and like ranging from like developing a new foundation model or fine tuning task or any reasoning on that geospatial um, task, or anything about like distillationing, like distilling the like large foundation models and like having a kind of like localized model for like maybe particular locations and things like that. So here we try to cover um, all aspects of foundation model. Like if you guys are interested, yeah, please consider submitting abstract here. To 30th July is the deadline. And they also support some travel grants, and they have a also virtual and like in person both. Like you can attend. Yeah, I'll pause it here for any questions. So.
Okay, thank you, Manikandan. Thank you for this engaging presentation, and especially thank you for showing the code, and also for this hands-on. I mean this AGU session which you just mentioned. So questions? Yes.
Hello, sir. I am Dipan Chakraborty from IIT Kharagpur. I have three questions. The first is regarding the mask. So what criteria did you consider to mask the data? I mean, in which points you are creating the mask? This is my first question.
Yeah, right. Actually, so we actually applied a random masking. So yeah, we didn't apply any strategic way. But what we try to do is like we try to like vary the masking ratio by 40 to 99%. And what we realized is that like around 50% masking was like it was giving a good reconstruction loss. So that's why we went with 50% masking. But yeah, it's a random masking. So
Oh,
one thing is like local and then the global. So that aspect we try to maintain it based on the window within a window or like across the window. Otherwise, it's a random masking.
okay, sir. And my second question is, what is this swing-like shift? It's I've mentioned here.
Mhm. Yeah, right. So actually, yeah. So this idea actually we borrowed from like swing transformer. So if you look at a swing transformer, so what they try to do is that right, instead of like doing this local attention, global attention, so they try to create a. So here you see the window is a non-overlapping window, right? So in a swing like shift, like what they do is like they try to have a like overlapping windows, right? So that way, like the given pixels will be part of like two windows. So that way it learns the global representation. So that's why we try, yeah, when you're not going to mask anything, right? So in that case, so this local attention may not be helpful because the local attention, the idea is to like, like looking at, I mean, since you have a like lot of like mask pixels, so you don't want to like look into one, I mean, pixel to pixel, right? So yeah, since yeah, for that, like yeah, there's no masking ratio. I mean, mask is zero, right? So they're not masking anything. So in that case, what we saw is that like applying this swing like shift, just overlapping window, actually, it learns both local and then the global context.
Okay, sir. And my third question is regarding the rollout. So while you are converting the normal model to a rollout model, did you change any strategy in training? Like, have you, yeah, that one. Have you started, I mean, consider calculating the loss after some of the rollouts in that way? Or did you get any, or did you train normally and the model started acting rollout?
Yeah, that's a good question actually. So yeah, in the rollout, yeah, so actually, yeah, there are like one more aspect here, as you mentioned, right? So maybe the first instant, like we try to mask, and then we try to predict the 6 hours ahead, right? So yeah, in the next consecutive steps, right? So there is no masking there. In the next step, like we try to use what is the predicted value goes as the input. Like so if you give a step of like maybe 24 hours, right, then there are like four steps, consecutive steps. So yeah, in that way, like first time we will be calculating that loss at the mask location, and in the next step actually we'll be calculating for all the locations. So only for the first step it will be the mask ratio be applied. Like in case if you have a more than like one more than like if you have multiple output step, right? So this data is like 3 hours data, right? If you are like a 6 hour head, so first 3 hour like we apply the masking, and next 3 hour we don't apply the masking. But yeah, next 3 hour we calculate loss at all the pixels.
In that way, it's carried on, right?
Correct, correct. Yeah, it's carried on. Correct.
Thank you, sir. Thank you.
Thank you.
Yeah, next.
Hi, sir. Thank you for the talk. I was just curious about your choice of data that is Mera 2 for training. I mean, like most models use Era 5 because you'd probably have a lot more data to train your model on. So I guess I'm just curious if you had some particular objective that you felt that Mera 2 would achieve better.
Yeah, correct. Yeah, sure. Yeah, yeah, so there's a good question actually. So yeah, the first reason, I mean, we started because I mean we started collaborating. I mean, this is actually in collaboration with NASA. So Mera 2 is from NASA, right? So that's the I mean first main reason. Like we wanted to see the like value of Mera 2 data set. But you are right actually. Like I mean, we can actually that is something in our like ongoing pipeline that we also wanted to include other data set. But some experiment we did like in the downstream task to see that whether really like having multiple data set really help or not, right? So we try to we pre-trained with Mira data set, but in the downstream task, like maybe I didn't show in this slides, but we have in the paper. So we try to see that whether it does good performance in the error data set or not. But yeah, what we see that it's able to actually do good performance in the other data set as well. But yeah, yeah, but we haven't yet experiment adding other data set in the pre-training part. But yeah, that is something we also we have included in our pipeline. Maybe we'll see that. Maybe yeah, we have to see that like how good actually that can also help. Yeah, well, the reason is like we are actually collaborating with NASA. Like they want to start with their the data source.
Hi, sir. I do have a question about the masking part. So it's interesting that you have used a masked input data to train the model so that it can learn to reconstruct the data. So how good is the performance in downscaling, low resolution data to high resolution data, like from global to regional scales?
Yeah, right. So okay, so okay, here I'm showing for zero shot. So the okay, so yeah, I didn't show the numbers here, but in the paper it is there. But yeah, we see that this kind of we did some kind of ablation study as well. It will be part of the supplement of the paper. So yeah, you are right. Actually, what we try to see that like how performance of just doing local masking and just doing global masking and combination of both. So yeah, what we realized is that like yeah, maybe yeah, local masking is actually doing better than global masking in terms of RMSE, but combination of both it's having a better performance. Um,
Thank you, sir. One more question is that, so this type of reconstruction application, can it be applied to other data sets which have a lot of missing values, like such as observations have a lot of missing data sets. So can we use this type of foundation models to reconstruct observations? What would be your opinion on that?
Yeah, that's a very good question, actually. I mean, that is one of the motivation actually to see, as you mentioned, right? So the missing data is sort of very common problem here. So yeah, that's one of the reason why we actually try to have a masking strategy to, do the reconstruction. So yeah, some of the charts you can see here, right? So we try to see that like if you do 95% masking, whether you're able to reconstruct it. Like yeah, at least for this case, like for U-turn feature, like we're able to see that it's able to reconstruct with just the 5% samples, it's able to like reproduce the like reconstruct the other 95% missing samples. So yeah, I think this is a very good candidate. Yeah, in my opinion. So
Thank you, sir.
thank you.
Anyone else? Let me just check if there is any online question.
Sure.
Okay.
Hi, it's a nice talk. I just want to know about the decoder architecture. So, I mean, for downscaling, what would be the input for that decoder? Or any how, because you have not you have not traditionally drawn any input to the decoder. So it's a multi-head. You told something like mask attention. Can you please elaborate some more?
Yeah, right. Yeah, so I didn't talk in the slides, but like we have some YAML files. So yeah, here actually you can choose your decoder. Like we tested with the unit, other decoder like FC and all. So, but what we see like mostly for at least for downscaling task, unit decoder is doing better. And yeah, in terms of the parameters, actually, yeah, so you can actually play with the parameters. So here, um, yeah, so here you can see that. Yeah, so these are the number of encoders and the embedding dimensions and all. So yeah, yeah, it's basically yeah, you can play. I mean, that is something like kind of hyperparameter, right? You can have a different decoders and then you can actually play with the hyperparameters. You can put like kind of hyperparameter optimization, right? Some kind of Bayesian, so you can try to see which combination of parameters does better for a given task.
Okay, if there is no other question, let's thank the speaker, Manikandan. We would have loved to have you on person, but nevertheless, thanks a lot for the talk.
Thank you, everyone. Thank you, Professor, for the opportunity. And thanks for the organization. Thanks a lot.